Okay, it's recorded. And now let's do some tutorial exercise. So this week we covered returning wall. Yeah. So we will do one problem in detail. So everything understanding. We did one in the class, but there was a little bit my system was not working and a little bit. Let's see if we can do very nicely one of those. Yeah. Let's do one. Please have calculator ready, yeah, in front of you, and then compute for me. I'm very lazy to calculate, all right? So I need to depend on you, okay? So 3, and let's open the lecture note because we need to see some formulas, right? 5 and 6, that one. Yeah, we'll start next week, the different topic, so that's all right. And then we need the tutorials, right? And then it is week 5, 6, retaining earth pressure and the retaining walls. There you go. All right, I also need something to write here. You can see my computer screen, right? Yes?
Yes, sir. Yes, sir. Yeah.
Yeah, keep talking. All right. Yeah, I feel bored if you don't talk. Yeah. I feel that you are not there or something. And then, all right, let's do. We did all problems. Only 2 problems left for returning wall, 5.2 and then 5.3. Okay. So 5.3, this problem becomes very huge. The reason for this becoming very big is there are different parts like we did in the class. Okay. But over here is a very small block and it's a vertical. So it may be a lot easier, right, to do. So there will not be that complicated type of problem in the exam, right? So it would be very simple block and then we try to use the concept. Okay, let's do question 5.2. Please make ready your pen, paper, everything to write there, yeah? All right. 5.2. All right, so what I do is the best idea for me is I just screenshot this and then paste there so that I know I don't need to redraw that, yeah?
Yes, sir. That's a good idea.
Yeah, because drawing this takes like ages, all right? Okay, so just that part. Maybe I'll all not answer, right? But just that part. Okay, good. Oh, not there in my presentation, right here. Look at this. It will be a lot easier for me, all right? I can't do these things in campus computers, so there you go. So now, oh, what is that? Not this one. Don't save that. And that's the one I'm trying to do. All right, let's do the problem. We'll look at the lecture note only if necessary. Let's start from here. Okay. So it's clear from here, right? You see, there is a surcharge. Yeah. So this angle is 10 degree there. And the first thing you need to check how we analyze this is because you need to find the pressure, right? Yeah. So we need to find whether there is a friction or not. Did you see that? That's a friction angle, right? Delta we represent by. Good. So that means we need to use what theory?
Uh,
Coulomb's theory, not Rankin's theory, right? Because that's the delta, right? Another thing is because wall is vertical here. Did you see that? There's a vertical wall, right? Yeah. So if the wall is vertical, yeah, then what happens is, and the friction angle there is an angle is applications, right? So angle is applications only this delta, right? So that means there will be a pressure at that. I don't know how I say that, delta, right? Yeah, can I check lecture note? I think that's what it is in the case, right? Yeah. So now, so that would be at the 15 degree, right? So applications is always with the friction angle. That should be written somewhere in the lecture note also if you want to see. Or is that? Is the Coulomb's theory, yeah? What that theory was somewhere there, eta. Yeah, that's it. Here should be. Yeah, that's it, right? You see, application is a passive. So if you see the active, it will be here, right? So active, right? So the delta angle it forms with the wall, right? Perpendicular to the wall. So that's good. So that's the case. Now what we need to find is we need to find, yeah. So it would be like this, right? The pressure due to backfill, yeah.
yes, sir.
Pressure due to backfill that. So we need to find this pressure first. And then we need to divide into two parts, right? One is vertical, yeah, one is horizontal, right? That's what we did in the lab too, right? That's the number one. But look at here, there is a surcharge load here, yeah? Surcharge gives what? Can I just draw outside of that so that I know what I'm doing? So it would give a constant pressure, right, throughout. Good, right? So that's what we need to find now. We need to find that and divide into two parts. For this, what it also acts at the same angle, right? That's what was the angle there at the 15, right? 15 degree. So that's a 15-degree angle X and convert into vertical and horizontal. Why it X is just because of this friction, okay? Nothing else. Otherwise, it would be horizontal. Okay?
Yes. Okay, sir.
Okay, that's it. So now we need to calculate now. Can you calculate now Ka using the we need the active pressure first coefficient Ka. All right. Okay. Oh, that is a long equation there again. All right. Yeah. And I go here and then just Ka, right? Coulomb's theory, not the Rankins, Coulomb's theory Ka. That's the equation. All right. Yeah. 11.3. Can you try now? So what is sine square? It will be smaller because sine square alpha is this angle. This angle is how much is that? 90,
Sine
right?
square.
Yeah.
Yes.
90 plus phi angle is 32, right? 32 divided by, I need K coefficient first, right? Sine square 90, sine square 90 degree, and then sine what? 90 minus, is it delta? Delta is
Yes, sir.
15, right? Yeah. Don't forget that, right? This is the square bracket there. So 1 plus, now there is a square root underneath, all right? So sine, what is 5? Phi is 32 plus delta, all right? Can I just write it straight away? 32 plus 15. How much is that? 47? Okay.
Yes, sir.
Sine
40.
Fine. Phi is 32. Take away beta. Beta is the slope angle. That one, right? Yeah, that's the beta. So that means the sine phi minus beta. Phi is 32. Take away 10 is 22.
Yes, sir.
Divided by sine alpha is 90. 90 take away 15 is 75. Yeah. So now sine alpha plus beta. So sine alpha is 90 plus beta is 10. Should be 100. And within that is the square again, right? Be careful with that. Okay, let's calculate how much we get, each of us. Come on.
So, I'm confused with so alpha is 90.
Alpha is 90 because it's a vertical wall.
Okay. Oh,
So how you know this is, please, yeah, don't just guess it. Just go here and see what is they assume these values. Did you see that alpha here in the diagram? That's alpha. Did you see that over here? Because it's a vertical, so alpha is 90. Is it okay? So beta is the slope at the top slope. That's the beta 10 there. And then what else? Yeah, just the delta is just the friction angle. That's it, right? Others we don't use, yeah. So always, please, because they use the different symbol for different thing, it's better to use for that particular theory, that diagram, all right, to understand. Yes. Okay,
Yes.
please compute that now. How much you got? Sine square 90 plus
0.315, sir.
you got 0.315, but we got 315. All right. So 0.315, right? Yeah. Okay. That may be all right. If I check here, they got 0.32. I think they just rounded up, so it's good. Okay.
Yes, sir.
All right. So we got Ka now. So what is this? How much is that? Come on. Who can tell me how much is that? Actually, I need to draw parallel to that, but I just approximately do. That is what? Ka gamma d, right? Yeah, that value is Ka gamma d, this length. Yeah. So now how much is it? Ka is how? 0.1315 multiply by gamma. How much is gamma? 18 times. And the depth, how high is the wall? Oh, I overwrote
4 meters.
so many things. 4 meters. Oh, I need to check here, right? That may be better. kilometer. Good. Can you calculate at the bottom how much is that now? This length from here, pressure diagram from this point to that point.
22.6, sir.
22.6. Please, other guys also verify. All right. Yeah. That's kilonewton per meter square. Right. Yeah. Meter square. That's it. So how about this? This is due to surcharge. Yeah. This is due to surcharge because you see the surcharge is 10. All right. That's the 10 value. So because the wall was not here, so I don't need to convert that. So straight you can do. So QKA, how much is that? You can also do 10 degree if you want. Yeah, just how much is this?
Choose 10. It's 3.15.
How much? 3.15?
15.
3.15, right? K is and that one. Yeah, 10. That's the 10 multiply. Okay, that must be all right. Okay, kilonewton per meter square. Now, this is the pressure diagram. Can we get the area diagram? Again, you can convert this to this horizontal also, right? Because the sloping backfill, but that is very negligible. We can ignore that. How much is the total force now? Area of that? 3.15 times 4.
12.6, sir.
12 point?
6, 12 point.
How much? 12.15 times, right? Kilonewton. All right, that's fine. Okay. If you consider that 10 degree also, there will be slightly different, but does not really matter when we use factor of safety 4. Oh, my internet connection may be lost or something. Okay, this is 15 degree. Can you convert into horizontal and vertical now? That particular one only. All right. So how much will be horizontal? So 12.60 times
Cos 15.
cos 15 is horizontal, right? Yeah, 15 cos equal to, so 12.17 is horizontal, 12.17 is horizontal. How much is vertical? Sine 15. Yeah.
It's 3.26.
Okay, 3.26. 3.26. So now I'm not writing unit because it's overcrowded here. All right. Okay. So this is horizontal and that's a vertical. We did for the surcharge case. Good. So now what I need to do is I need to find the area of this triangle for this. Come on. How much that would be? I will remove these all other things, right? Otherwise it will be too crowded there. All right. Yeah. Here you go. KA, what we got was 1 point. Yeah, that's fine. All right. Now, how much is the area of the triangle now? This total? 0.5 times 4
45.2.
times, what's the bottom? 22.6, right? 22.6, right? 45.2. Yeah, that's the angle. Yeah. And you need to convert into vertical and horizontal again. That too. All right. Because that's the angle is 15 degree again, right? Because fix an angle. Times 15 cos equal to 43.66. What that you got? Yeah. 43 point. Yeah, come on.
43.65. Same.
Yeah, 43.65 horizontal, and then vertical one is
11.72.
11.72. Thank you. Right, that's it. So we already, from the backfill given, we already calculated all horizontal and vertical. Yeah, easy, isn't it? Yeah. So now what you need to do is now, because of the self-weight, I need to divide this into, this is very easy wall, only 2 parts, right? Look at this. That's the one rectangle and that's the one. Can I write this as a 1? And I write that as a 2. So how much the vertical here now for the 2? W2. What is the weight of that?
0.5 into 4 into
W2 is 0.5 times 4 multiplied by, what was the density of concrete?
I think
24, right? Yeah, 24. That's what we got. That's the area times density, because per unit in the other side should be enough. Come on, how much is that?
48, sir.
Yeah, of course, yeah, the half is 248 kilonewton. That's fine. Yeah, good. So now that's a 1. I need to calculate that one also, W1. So it's the area of triangle. So half, base is how much is that? 0.5 is 2.5. Yeah, base is 2.5 and height is 4 and times 24. Can you calculate that triangle part weight?
Yes.
120, sir.
120 kilonewton. Oh, that's the big one, right? Oh, come on. Where is that? Yeah, 120 there. You see? So now we got that weight, right? So now your job is looking at this, right? Now we need to find whether there are 3 cases to check, right? Number 1 is sliding. Good. Number 2 is overturning. And the third is bearing capacity on the bottom. So because this is very small part, right? The passive pressure we can ignore. Okay, it will be more safe if you ignore the passive pressure, all right? Okay, so that's why we try to ignore that part. You can calculate, but that is not necessary as long as it's small. But if like this part is like this, very high, then we need to calculate because this is a huge, right? Of course, who makes wall putting both side backfill? Yeah, that's not that common, isn't it? Yeah, so just ignore that part. All right, so now, so this is the point where you need to check. All right, this is the point where you need to check all those calculations, right? So now first let's do the sliding. All right. Oh, I want to see this data, but I need to go to the next page. How I do? All right, can I open another one on the left side? Please, oh no, that's the same one. So I want to use this, maybe my lecture note one page there. Okay, somewhere here. Yeah, so that I can see side by side. Yeah, new slide there. It's all good, right? Yeah, so move this side and just delete that. All right, I'm on the right here. Okay, so that's the reason why side by side is a lot easier. Okay, now, so if you calculate at this point O, that point O, like this is the toe of the wall, that. Now, your job is first check the sliding. One is sliding. What are the sliding forces? They're disturbing. What forces makes this wall move that way? What are them? Horizontal component of that? Yeah?
Okay. Yeah.
And then horizontal component of that, right? They push the wall out of the backfill, right? Yeah, it goes this way, yeah? The horizontal component. So the disturbing, can I write like a sliding? How I write that? It's just a disturbing force, right? Yeah. So it is, how much is that? That's the disturbing, what? Sliding force. Okay, I'll write, yeah, that's the one, force. So it would be 43.65 plus 12.17. Can you calculate that for me? That's how the sliding force, it helps to push the wall out of the backfill. How much is that?
It's 55.82, sir.
55.82 kilonewton. That is the force pushing the wall out. What is preventing? Resisting force. What is preventing? You see, there is a vertical weight going down, right? It gives some friction along the wall there. You see, that's what we need to calculate. Can I just highlight that? Friction over here. Yeah? So friction, to find the friction, we need to use the friction of the base, this 20-degree angle. So how much is the total vertical force now? Can I do total vertical force? So first one is 120. Can I write that here? So 120 kilonewton plus 48 kilonewton. That's because of the concrete. But there is a backfill. How much is the vertical here? 11.7. Is it 7.2? Yeah, that vertical part of the backfill is 11.72 plus how much that other vertical part? 3.26.
Yeah.
Is there anything vertical force?
About third chance. No.
surcharge is out of the wall, right? This is already we calculated pressure here. So if it is within the part of the wall, we need to do like yesterday we did, yeah? But this is out of that. It's just the backfill is considered here. All right, good. So can you add them together? How much is the vertical force first? It's not resisting force, just the vertical first.
It's
Vertical.
182.9, sir.
182.9 kilonewton, right? Now, because that's the vertical, do you remember how the friction works? If this is the vertical, yeah, this is the vertical force, and this is how along this, we need to calculate the friction. So just mu V, right? That's what it gives the resisting force, right? Friction force, right? Mu is just 10 pi. So can I calculate now resisting force? Resisting force equal 182.9, 10, mu is 10 phi. 10 phi is 20 degree. Can you do that for me, please? Yeah.
Yes.
182.9 times 1020, okay?
66.38.
66.38 kilonewton. You see, that's that much resisting, right? That provides here. Can I just draw that much force? It provides this side, X this side. You see, that much is pulling, that much is pushing in. What is factor of safety now? For sliding. Factor of safety always resisting is 66.8 divided by 55.82, right? That's the resisting, isn't it? Right? So yeah, that's a sliding force, right? This is the resisting force divided by sliding force. How much is the factor of safety now for sliding?
It's 1.18.
1.18. You see, that's very small, right? May not be enough. This wall may be moving, right? Yeah, sliding. The reason is because it's just very small part in this side, isn't it, right? And then there's a sloping backfill, right? So that's why that is pushing a lot. Maybe we need to have a little bit cantilever, those type of things there, right? Yeah, it looks a little bit risky, but that's what we got. More than one is okay. And also we ignore the passive side, this side. So maybe this provides a little bit more safety, right? But that's what it is. What the answer they have? We have here. Yeah, 1.18, yeah? That's it. That's for sliding safety. Good. What is next? Overturning, right? Let's check overturning. Yes. Okay, so now just insert one slide here because I just don't want to move that out because I need that information there. New slide there, yeah? So just move that out and then put that in, right? Okay, so here you go. So second is what we call is a rotation, right? Rotation or overturning?
Overturning.
So both same, all right? Okay, rotation or overturning. So what you need to do is now, okay? So can I just remove this, what I explained thing, right? Now for the other things, oh, I need these two, right? Yeah. So don't delete the other things. So, okay, keep that there. Yeah, that's the one, that's the two. So at this particular point, you need to calculate moment. Moment going that direction, a moment going other direction. Yeah, do you understand? So one movement is trying to twist the wall. Yeah. Another direction says it is trying to save the wall, right? Can we calculate now all of those? So first the horizontal forces, right? Yeah. Now let's start from this one, overturning moment. Okay. So MO, sum of all MO. What happens? It start from what will overturn, what will help to overturn that is both horizontal forces, right? That horizontal as well as that horizontal. So how much is that? First horizontal 43.65, right? That's the first horizontal. How far is it is acting? You need to multiply. How far? 4 over 3.
4 by 3.
Good. That's good, right? Because that's 1/3 of the triangle, right? But for that, it acts in the center, right? Yeah. Plus another is what? 12.17 multiplied by what? 2? How I got 2 there? Because that X in the center is a rectangle, right? Center acting point is in the center, right? So that's
Okay.
it. How much is that overturning moment? I think there is no horizontal thing now, yeah? Only 2. All right. How much is the overturning moment? I'm calculating this, right? Yeah.
82.54.
82.54 kilonewton meter, right? Because that's the moment, right? So how about resisting this side, m_r, going the other side? Yeah, how much is that?
Yes.
So now what will help to go that? That's the weight first. How much is the weight for 120? Multiply by, how far is that from the point?
It's like 2 into 4 by 3.
2.5 divided times 2/3. Is that make sense? 2/3 directions from that side, right? Yeah, can I just point out somewhere here it X, right? 1/3 in that direction is a triangle. So this whole distance from here is 2.5, yeah? So 2/3 of 2.5, makes sense, yeah?
Yes, sir.
What do you think, right? Go to for the second one, rectangle one. Rectangle 48 times where it X in the center of that, yeah? So 0.25, 0.25 less than 3. So 2.75. Are you with me? Yeah, we need to find the area of the what they call location of the applications, right? In the center of the rectangle, right? So what
Yes,
else?
sir.
Oh, there are vertical also. Yeah, keep going. The vertical force is 11.72, 11.72. It acts on the surface of the wall there. So it's a
Excuse me,
3.
sir.
Yeah.
The 2/3 you have taken. We need to 2.5. It's okay. There is 2.5, man. 0.5 is.
Yeah, because this total is 2.5, right? Within this, right?
Yeah.
So it acts 1/3 from the base, right? Not the top,
Yeah.
right? So 2/3 is from the other side. Yeah. Is good?
Yes, sir.
All right. So now another one plus, right? So this one is acting what? 12 point, oh no, that's the horizontal, right? Vertical is what? 3.26, is that correct? 3.26 multiplies also on the face of the wall. So that means 3 again. Can you compute the resisting moment?
Yes, sir.
All that helps to prevent wall from rotating, okay? So that's what the resisting moment is all about.
Is it 376.9?
376.9 kilonewton, yeah?
Yeah.
Yeah.
Other student also got the same meter also, all right? So what is factor of safety now? Very easy, right? Factor of safety for overturning is, what is resisting is 376.9 divided by 82.54. Oh, it's a big one. It does not rotate, yeah?
Yes,
Can you compute that?
Yes, nearly 4.6.
4.6, you see? That's a big one, right? Because this is a big factor of safety. So this wall will not rotate, but there is a chance of sliding because factor of safety against sliding is small. Yeah, I know that's because of the no passive on the other side. Yeah. So can I check the answer? What is it? 4 point. Yeah, that's very close enough. Yeah. All right. Yeah. 4.53. That's good. What is the third?
Bearing of okay.
Bearing, yeah, at the bottom, what will be the bearing pressure, right? Yeah, so can I put another new slide here so that I can refer to those data all the time? Yeah. But now let's do the full way, right? So now what you need to do is you need to find first, right? So can I draw that wall now? Okay, so little bit because I need to redraw again. So that's the wall. Oh, look at my drawing. Yeah, not good, right? So because, can you see that? Yeah, okay, that's the two parts there. Because in this case, what is happened? This is from here to here is 3 meters, right? Yeah. So now there is a little bit of vertical load. If I calculate it, it goes, how much is total vertical load we calculated? Somewhere we did. Total vertical load, everything. 180 something, I don't know.
82.9.
Okay, 182.9 is going there. Yeah. And then moment. So that side of moment is how much is that? So 82.9. So this side moment, right? I'm talking about all resisting now, right? We need to find the center of that load, right? That one. How much is that? Oh, come on. Moment, this side moment. How much was that resisting moment? We just calculated before. So you can do the total moment, right? So total moment this side, right? Because another this side moment was how much that? Come on, yeah, I want to check.
One is
That side moment is 82.54, right? That is 82.54, right? And that side is what?
376.9.
376.9. So overall, the moment will act this side, right? How much is the difference between these two, right? That's what I need that for eccentricity. Can you calculate that? The 376.9 take away 82.54.
294.36.
So 2, right? 100 or 200?
194, sir.
194.26, is that correct?
294, sir. 290.
All right, okay. So I didn't press. So that's it. So that's the vertical force. Now we can calculate where this force will act. So moment divided by vertical force. Okay, that's the location, right? From here, where that force will act. Can you calculate that now? 294.26 divided by 182.9. How much is that? How long is the distance it takes?
1.6.
Okay, 1.6 meter, right? The meter. Now, remember, from here to here is how much is that? 3 meter? Total is 3 meter.
Yes.
It acts in 1 point, how much? 1.6, right? Yeah. So a little bit this side of the halfway through. Make sense?
Yeah.
It's good, yeah? So you know that now, right? So that means X bar is, can I just not show this, right? Yeah. So this is 1.5 that, but X little bit this side, right? So total is 1.6. Look at the eccentricity now. How much is eccentricity from center to that?
0.1.
0.1.
That's it, right? Now, once we know the eccentricity, now we need to calculate. So because it's pressing this side, so this side would be, when it is overturning that way, 1.6 from that side, right? So what happens is this side is 0.1, right? So maximum and the minimum we need to find. So if it takes that side, so it would be smaller, yeah? Yeah, so now can I draw at the bottom because we already know the eccentricity? I want to draw the pressure diagram here. So one is because this is Q max, yeah? Another side is Q minimum, so there will be a pressure distribution at the bottom, all right? That's how it pressures, right? So this is Q max this side, and this is Q minimum this side. All right, so how much it would be? There you can directly use the formulas, right? Can I go there now?
Yeah.
Yes.
So you see the formula because we know the eccentricity of loading, so you can calculate directly what is Q max and a Q min based on this diagram, right? So can I go and have a look? Where is the Q? Oh, that should be somewhere there.
160 by B.
And that one, right? Did you see that here? You see sum of all vertical forces. Can you write this Q max and a Q minimum formula, please, guys? Yeah. For your case,
Yes.
Q max equal to summation B by B 1 plus 6E over B. Q minimum is summation B by B 1 minus 6E over B. All right. Can you write these two formula for me? Yeah. Maximum is that, and the minimum is that? All right. I think it's not easy. One is plus, another is minus. Yeah. All right.
Minus.
Let's go back to our problem. So now here. So now Q max equal to, okay. Oh, summation B, I removed that. So hopefully you guys can give, right? So Q max equal to how much is the total vertical forces?
182.998.
On 9. Okay. Divided by, I think B, right? B is the total width, which is 1.5. Yeah.
Yes, sir.
1 plus 6, E we calculated 0.1 divided by 1.5. Is that make sense? Yeah, is okay? Yeah.
Yes, sir. Yeah.
Can you calculate Q max there now? Maximum pressure, right? The Q minimum is the same, but less, just a slightly minus there. So 182.9 divided by 1.5. Oh, B is not 1.5, B is 3.
3, sir. It's
Yeah, all right. Hey,
Good.
look at this. Because all width we need, come on, yeah, 3 there.
1.5.
Yeah, 3 there. All right, okay, so all 3. All right, yeah, so now, so 1 minus 6 times 0.1 divided by 3. Of course, width is 3, right? Total foundation width. All right. How much you got maximum?
73.192.
73.192 is the pressure, so kilonewton per meter square. Yeah, maximum pressure is 73. Yeah, and then minimum pressure is
Kilonewton.
just minus there. Every data is same. Yeah,
48.79.
48.79 kilonewton per meter square. Good, right? Yeah. So now that much pressure, maximum pressure is giving down, right? What do you need to know now? You need to know how much this swell can carry up, yeah? Bearing capacity now, all right? And to calculate factor of safety. How we calculate bearing capacity of this swell now from here? Week 1 and week 2, lecture notes, all right? Okay, so let's keep moving now. Let's use one of the methods, right? Over here, they use Hansen. So let's see Hansen, bearing capacity foundation. Bearing capacity of foundation, right? Yeah. All right. So let's use one of the methods, right? Any methods we can use, right? Those available. Now, is that what is our problem? Is it C5 swell or just C, or what is that? There is no C, yeah? Coarse grain swell. That means, what are the formula for that? Can we recall that? Yeah, so let's use one of the methods. So Q bearing capacity, QF, ultimate bearing capacity is equal to, what is there? I think what? CNC plus gamma dn, gamma dnq plus
0.5.
half b
Gamma B and gamma.
half b gamma and gamma. Is that correct? Without correction factors for now, yeah? All right.
Yes, sir.
Okay,
Yes,
so
sir.
yeah, I think, but I haven't written correction factors here. All right. So we will use those, but for the retaining wall, guys, yeah, for the retaining wall, correction factors all take 1. They have suggested. Okay, so I don't need to take those things. All right. So that means, so this is 0. Why this is 0? Why this is 0? Because this is coarse grain soil. C value is 0. Yeah. Did you see that? Yeah. C is 0.
Yeah.
This would be 0. Why? Because we ignore this. You remember we ignore this. So it is based on the surface of the soil. Okay. The concept is there is no depth. We put the foundation below the surface, right? Because D is 0. Yeah. In that case, because if you put the bottom of the foundation on the surface of the soil, also middle term is 0. So only we need to calculate its last term. Is it? Yeah, how easy that is? Half. What is the B? 3 meter width. What is the gamma at the foundation? 19?
19.
Yeah. In gamma, so I need to find n gamma based on phi 34. So phi 34, right? Phi equal to 34 degree. Can we check some table bearing capacity? Any methods, right? Okay, let's use one of the methods. Can I go to the slide? What is the n gamma value for 34? Week 1, yeah? What is week 1? 1 to there, all right? So I want to just get that one table, maybe just use one of the methods, right? Yeah, you can use the correction factors too, but I'm not going to do that now. Yeah, so let's check one of the theory, Hansen theory, right? That's the table. 34, is it? 34. So n gamma is what? Which one method? Hansen. Let's use the Hansen one. Yeah. So now can I just point out where I'm talking about? Yeah. So that's the Hansen one, n gamma. Yeah. So I'm doing for 34 degree. Well, how much is that?
28.7.
28.7. But if you use little bit of other correction factor, it will be a little bit different. Okay, don't worry about that. Just do the straight one, 34.28.7. Can you calculate that for me now? How much is the ultimate bearing capacity?
$817.9. Hello.
Ah, please there, 28.7, right? Yeah, 28.7. So 81, tell me, 81.
7.9.
817.9. All right. Maybe we need to little bit because it looks quite big, right? Bearing capacity. So we need to check that because we may need to little bit use some of the correction factors. The reason may be, can I have a look? Because this is the angle load, right? Load is angled, right? So it's coming in that angle. Oh, we gotta use, right? For now, let's leave it for now. But you see Hansen method, can I go a little bit down? I think if we use angle, so it would be a lot less, right? There is what is the angle of correction? Load inclination correction, right? Where is Hansen? This is Hansen, right? Yeah. So yeah, they also have the inclination corrections, right? Did you see this NQ? But for Terzaghi, there is nothing, right? Yeah. But if you write here Terzaghi equation, that's done already, right? So how you calculate factor of safety? Let's say we did the Terzaghi one, no corrections, right? Yeah. So how much is the factor of safety for bearing capacity now? This is how much the pressure it can hold, 817.9 divided by, what was the giving pressure, maximum giving pressure to the foundation? Oh, wow. What did I write that? I wrote somewhere. Yeah, here you go. Maximum is 73.192, right? How much is that? Oh, factor of safety is used 10 around
11.2, sir.
You see, that's it, right? But this is only based on Terzaghi theory, right? That one. So if we use Hansen's or other corrections, it may be slightly different. How you feel? It's okay? So in this solution I have provided to you guys, I have used Hansen, so there is a little bit multiplier point angle of load inclination, because you remember, because load is coming in angle, right? Yeah, because all over their angles. So that means you need to calculate that angle and correct for inclination factor, right? That changes this a lot. And so you get a little bit different factor of safety. My suggestion to you guys is, if nobody says you use this method for foundation bearing capacity, you can use very simple, any method, right? But if it is specified, use that method. Is okay? Yeah.
Okay, so yeah.
All right. So, but I think in the solution provided, we have used the Hansen method. So we need to find this I slope inclination corrections. All right. Okay, that's it. How about another question now? Yeah, I think we are done that, right? It's got very high, but solution provided here. You see, these two are correct, right? That one is a lot exaggerated estimated because we just use the bearing capacity Terzaghi method, right? Yeah, the solution is based on Hansen method. Did they say anything to use? Nothing, right? So does not matter. All right. Even for this case, if they use Hansen method, it's still factor of safety more than 4. It's already safe. Yeah. How about second problem? Exactly same. But there will be slightly different things. Why? Because there is a weight of the what swell also here. Is all right? Okay, let's do this one. Again, I'll not do the bearing capacity part because that's already done. So I'll do just few sliding part. Print. Where is my pen? So I'll copy that and then draw the diagram, right? Will be. So now I can draw this, or maybe I'll just remove this and I'll check because I need some space to draw there. All right. All right. So now just remove this also. So I need some space to draw clearly the diagram, right? So just cancel that and then copy this. Again, when they say determine the stability of analysis, that means you need to just do those 3 testing. Good. All right. So let's do now. Which one? Let's do here. All right. So now I paste here the retaining wall now. And then I want to ask you guys now, yeah, to teach me here. All right. So because this is cantilever wall, so always we calculate the lateral earth pressures over here on the face of the wall. Good, right? And do you understand that, right? Before, because there was no cantilever here, so we calculated over here in that face of the wall itself. But in this case, we need to calculate over here all pressures in this line. Oh, before also there was a slope, right? Do you remember what we forgot a little bit? We forgot to compute that part, right, in the first problem. I think weight, it is giving a little bit of weight or no? It will not give that weight. Why? Because we were calculating pressure over here. Do you understand? Because there was nothing other side. But now, because of this, we need to compute that small part at the top also. Is it clear or I confuse you now?
Yes, sir.
All right. Okay. So now, so that's why, because we are calculating here, the pressure is in this vertical line from the last point of the wall. So there is a one little bit weight giving by that ways also we need to consider. All right. Okay. And also more than the before, what we need to do is we also need to consider this swell weight. And I divide into few parts now. This one, that's the one. Good. So there is a triangle here and a one rectangle like we did before, right? Let's say this is number 2. That's number 3. So this swell also gives number 4 there, weight there, the swell itself. Yeah. And also the small part there is 5. Good. Look at the component we need to consider here. So 1, 2, 3, 4, and 5. There are other component. There is only one other component. There is what? There is a pressure giving here. Good, right? From here, not the top, right? Yeah, at this point. Okay, come on. My drawing is so bad. I don't know whether you guys should go there. Vertical line from here, all right? All the way through. So you need to calculate that part. All right. Is this friction given in our problem? Yeah, again, we need to calculate what? Ka coefficient based on Coulomb's theory. Can you please, guys, yeah? Can you calculate Ka giving the same equation? Don't waste time now calculating. You will guys calculate. Can I use what I have here? Is okay? So I have here, no, not that one. Of course, you can calculate that, right? I have K is 0.33 here. All right. Oh, this is 30 degree, yeah? 30 degree is a lot easier. So Ka value is 0.33. All right. So who can tell me now how much is this? Ka, comma, D. Yeah, so can you compute now? How much is it? K is 0.33 times what's the gamma?
Gamma is equal
I'm
18.5.
19, sir.
No, at the top, you need to check backfill. This is for the base, all right? Base we will calculate only for bearing pressure. So 18.5 here, all right? Yeah, times, what is the depth at this point? Oh, I need to calculate. So 1 there, 6
Six.
there, not 7. There is a little bit at the top also, okay?
We need to calculate, sir, for it. Like we need to use the triangle.
Yeah. So now, so this, we need to use that triangle. So this part is, how much is that part? 4.5. Oh my goodness, they didn't give it straight here, right? So we need to calculate 4. That's a 1.2 less, right? Yeah.
5 minus 1.2 minus 0.5, sir.
Not 0.5. There is
Oh.
still a triangle there, so we need to minus that too. I don't know how much is it. What is 1 in 20? Yeah, 1 in 20 slope. So now total is 6. Okay.
0.3, sir. It's
So just wait. Yeah, just I want to confirm that, right? So 0.5 is at the top, right? Yeah. And so 1 in 20 means 1 is 20. So now how much will be 6? 1 over?
6 over 20, sir. 6 over 20 is equal to 0.3.
6 over 20, 0.3. So this part is 0.3. Yeah.
Yeah.
And that part is
0.5.
0.5. Yeah. Correct. So total is 0.8. Oh, that makes sense. 0.8 there. Total is 2 from here to here, and then it's a 4.5. So that means it must be 2.5. Yeah.
Yeah.
Okay. You calculate from geometry anyway. So now use triangles to find this little bit extra height there. So that means that's the height we need to calculate. So 2.5 is this, so that divided by 10, yeah?
Based into height, sir.
Yeah, height is 10, right? 10, 8 degree, right? That's a 8 degree, yeah? All right.
Yeah. 10,
Okay. Yeah, 10, 8. Yeah.
8.
So 10, 8.
Sir.
How much is it?
35.
0.35, yeah? Is that correct? Yeah? 0.35. Okay, so now this is 0.35. From here to here is 6. Yeah, that's a 0.35 there. And then there's a 1, right? At the bottom is 1, yeah? 1. Okay, good. How much is total now? 7.35, yeah?
Yeah.
Oh, that's a long height. Yeah, 7.35. Okay, big. Can you give me that number now? Here at the bottom.
0.33.
4.87, sir.
For 4.87 kilonewton there, right? That's the bottom part. So I need to get this right now. So this is the force I need to calculate now, area of the triangle.
It's like 10, how many degree?
Yeah, so no, this is what delta degree. So it's a 20 degree. Yeah,
Yeah.
okay. So that's the horizontal is 20. That's a 20 there. So this is
Yeah.
the horizontal force. That's the vertical force acting there. All right.
Sir, it's 44.87 into cos 20 degree, yeah?
Is that 40? No, because you need to, this is just the pressure at the bottom. You haven't calculated the area. You need to do first 0.5 times 44.87 times height. Height of the wall is what? 7.35. Yeah. Okay. So calculate the force, total force. Okay. Yeah.
164.9.
164.9, right? 164.9 kilonewton there. Now you need to convert into horizontal and vertical.
Yeah, it's like 164.9 cos 20.
Cos 20 gives this, and then sin 20 gives that.
20. Yeah, horizontal equal to vertical 164.9.
164.9, right? 64.9 times 20 cos, right? 20 cos.
154.95.
Oh, can I write 155? It looks like very big, right? Okay, very easy to write that. Yeah. So do the other part, the vertical one.
It's 56.4.
Okay, can I just 56.4 kilonewton? All right, so we got this already based on the hill. But now I need to calculate weight of this wall. Okay, W1, W2. Can I do now the weight of 1?
Yeah.
1 is what? What is the total width at the bottom? 4.5?
4.5 into 1.
4.5 multiplied by 1. Yeah, and then times density of concrete.
Yeah, 25.
Where is
24, sir.
Sure.
It's up there.
Oh, okay. So 24 there. I didn't see. They wrote on the right side. Okay, 98. So this is 98. I'm not writing unit for the moment, all right? Because there's too much space it covers.
Sir, it's like 4.5 into 4.5, sir. It's not 4.1.
So 4.5 times 1, because that's the depth is 1, right? Times 24.
24, yeah. It's
Oh, 108, yeah?
Yeah.
Oh,
W2 equal to
108. Or W2. Let's do W2 first. Okay, W2 is half. How much you said this was before?
0.3. 0.3.
0.3. All right. Half base is 0.3. Height is 6.
Yeah, it's 0.9 kilonewton.
0.9. 24. Multiply by 24.
Oh, into 24. It's 21.6 kilonewton.
All right. Okay. So W3 now. So multiply 0.5 times 6 times 24.
W3 equal to 1.5
48. 48.
into
48. Yeah. Somebody got 48. Yeah. Check, guys. Yeah. You keep checking. And now can we calculate W4? Giving
0.5 into 6 into 24 is 72. W3.
72.
Please
Okay.
check it.
Yeah, please 0.5 times. Yeah. And then that's a 6 times
Times
24.
24.
72. All right. Okay. So W4 now, weight of the swell here. So that means what is the size? 2.5 by 6. Yeah. 2.5 by 6. 2.5 by 6. I wrote 2.6. All right. 2.5 by 6. Okay. Multiply by the weight, the unit weight of swell. 18.5.
19, sir. 18.5, yeah.
18.5 in the backfield. 277.5. Oh my God, that's a big one, right? 277.5. And W5 at the top. Oh, that's a very small probably, but we need to calculate anyway. Let's see. Half, right? 0.5, and the base is 2.5, right? 2.5. Height is, we just calculated 0.35, right? Multiply by, that's a backfield, so 18.5. 18.5.
8.09.
I wrote wrong, so 0.5. Can I just check, right? 2.5 times 0.35, 35 times 18.5. So 8.1. All right. Okay. Look at this. How small that is compared with the bottom one. Yeah. 277 and 8. So we got all weight, everything ready now. Yeah. So now we just calculate these 3 factor of safeties, right? It's really easy. All right. So now, what are the sliding forces? Only this, yeah? There is nothing pushing this side, right? Yeah, nothing pushing this side. Only that, right? That's the only thing that is pushing. How about, so friction here now? This part, total vertical force, how much is total vertical force? Can you guys calculate summation V? Add all of them. 103, that, all up to 5, as well as you add this, 56.4.
Summation B equal to
Everything, add them all, these all 5 words, as well as there is a vertical component of pressure. Oh, that's not 15, it's a 155, not 15.5, right? That's a big number. All right, okay, here you go.
1 plus, so 56.4 equals to vertical force, and the triangle load we have added. Just we should we need to add a 56.4, yes, sir?
Yeah, total, all
Yeah.
weight and then 50.4. How much is that total?
108 plus 21.2
Total vertical force, yeah.
plus 8.1 plus 56.4. It's 543.6.
543.6 kilonewton, right? That's what it is giving from the top. And
So-
then we need to calculate the friction. This is now 10.5. We need to do the resisting. Okay, there is no space to write here. Come on, yeah. So let's do that now. So that's the resisting, right? Yeah. So if that is resisting, how much is coming here? So that means mu. What is phi? phi base is 20 degree, right? Friction at the base is 20. Yeah. So friction at the 20, that force. So can I calculate the sliding, resisting sliding total? So 543.6, 543.
Sliding resisting SR equal to
43.6 and 1040, 1020, right? 10.5, right? Mu is 10.5, isn't it? Yeah.
sorry, sir. Can you explain again?
So always this is along that, right? Something is vertically pushing down, right? And then if there is a friction angle there, so that means this force, vertical force, right? Let's say V, right? That helps preventing this from sliding.
Okay.
Okay, so that means this is vertical total V multiplied by 10 friction angle.
Okay. Summation V multiplied by 10 and 5B, yes, sir?
Yeah, that's it. So 5 is 7.
And how much it is? 543, 543.6, 10, 20. It's 197.85.
Anything others impacting? So horizontally it is pushing, that's resisting, right? Anything other going in the, oh, did we add this all, right? Yeah, we add all, isn't it? So
Yeah.
this includes this vertical also, isn't it?
Yeah, sir. 56.4 included.
Included, right? Okay, so why the solution is slightly different here? Oh, that's a short term. Okay, that's all right. Okay, so did it? Okay, that's fine. So there are two things done here, because did you see this two factor of safety here?
Yeah.
We call it like a short term and long term. Short term is when we have C, but there is no C here. It looks like granular field, right? Okay, let's do only one case. All right. So how much you got?
It's 197.85.
85, that 197, right? 0.85 kilonewton, right? So now, so this is what? Resisting, and that is pushing. What is factor of safety now? So this is pushing, and that's resisting, right? Can I do that now? Can I go to the next page? Right, here I go. So factor of safety, sliding. This is, we call it like a, so now sliding is, how much is that? 197.85. 197.85 divided by
155.
155. Yeah. How much is the factor of safety? I think we should get
157.
How much?
1.3.
1.3.
3.
Okay, so that's the first one. Yeah. Okay. So that's all right. Okay, so that's the sliding. How about how we calculate the moment again? Same as before. So we calculate moment at this point. You understand, right? How many? Maybe we are not doing now, right? So you calculate all that is moment that way. So that means only this horizontal force will do that, isn't it? Right? All others will resist. So what is the overturning moment? Second is rotation. All right, yeah. So overturning MO, overturning moment is, how much is that? Over here is 155 times where it acts. How much distance is 1/3 of 7.35, right? That's the location it acts, right? So 155 times 7.3 divided by 3. Can you calculate overturning moments now? The force that helps turn the wall this way, right? That way. That's overturning moment, right? So 155 times distance from the center at the bottom. So it should be, total would be 7.3, right? 35, right? Sorry, not 3. 35 divided by 3. 35. Can you calculate overturning moment now?
155 into 7.35 divided by 3. 379.75?
397.
79.35.
You see, that's it. It's a kilonewton meter, right? That's the overturning moment. How much resisting now? So now you need to check each of those, right? It starts from 1. So 1 is from this distance is midway through, right? 4.5 by 2. So how much is the weight? 103 times 4.5 over 2.
108, it may be 108, sir. Not
108 times 4.5 over 2, right? Halfway through. That's the first. How about the second one, W2? W2 is this one. So area was 21.6, right? The 21.6 load
Into
times how far the force acts now.
1
One third of that, right?
plus
one,
1.2
two-third of that,
plus
sir.
1.2 plus 0.2, 1.4. Makes sense? Yeah, because this is 0.3 at the bottom, right? It takes 2/3 from this top. So 2/3 is 0.2, 0.2, 1.2, 1.2, 0.2 is 1.4.
1.2 plus 0.3 equal to 0.5 into 2/3. Ah,
Okay, check again. Okay, so now we need to find here, right? That's location, right? The force. So in this case, this is 1.2 already there. So this is total is 0.3, isn't it? Right? Total 0.3 means this side would be 0.2. Other side would be 0.1. So that means 0.2 plus 1.2, 1.4. Makes sense. Yeah.
Yeah.
All right. So that's the second. So what's the third one?
72 into
72
1.7.
multiply by, so that is
1.5.
0.3 there, right? So 1.5 and 2.5, 1.75.
Yeah.
Does that make sense? Yeah, 1.7. 72 times 1.75. All right. W3 done. What's W4? W4 is that one. Yeah, that's an easy one, right? Okay, so total is 2.5 there. Oh, we need to find. So W4 2 is 27.5. Yeah, 227.5 to 27.5 times location in the center. All right. The center of that is this side is total is 0.8. This is total is 2. 2 plus 2.5 by 2. How much is that? 1.25. So 3.25 makes sense? 3.25? Oh, I don't know. Yeah, you need to check that, right? 3.25. I think so, because total work from here to here is 4.5, right? Take away 1.25, right? Yeah, 1.25 take away, because I need to get the center of that, right? I think this makes sense. 1.25, 4.5 minus 1.25, 3.25. Okay, good. Plus, what is we done? W4 done. W5? W5 also, oh, location will be different. There you go. All right. So now W5 is 8.1. 8.1 times. Okay, so that side is what? Total is 4.5. Total is 4.5. Take away 1/3 of 2.5. 4.5 take away 2.5 over 3. Anything else we need? What is resisting? Oh, there is a vertical force by the backfield, right? Yeah. So what is 56.4 plus 56.4 times where it is acting is 4.5, right? Face of the wall. Yeah. Please do this calculation for me. Resisting moment. All of those. Please.
So for now, just to use the calculated one, it's take a time.
Yeah, that may be better, right? Of course, the solution is here. So over here, what I have here for overturning is 1584.
Okay, right, just 1584.
So now what is factor of safety now? Factor of safety equal to? So resisting moment divided by overturning moment. So now what? 1584 divided by overturning is what? 380. Okay, I'll just write 380 approximately there. Yeah.
4.16.
4.18. Did you see that second one? 4.18, 4.18. 16 or whatever we got. It's same process we explained, right? Just the different, too many components here to calculate. That's it. Yeah, nothing else. I think we will not continue anymore, right? It's the same process, right? I have done the solution here. You can see. And then what is the third left now? It's just the pressure, right? Yeah, again, I'll just give you the idea. This is 4.5 total. One side would be more pressure, another side would be less. Yeah, so there is an equation to compute, right? Which side is more and which side is less. So if you compute the maximum pressure here, this is Q max, and there's a Q min here. So once you Q max, and then you need to calculate how much swell can support. You see, so that the bearing capacity divided by Q max will give the factor of safety. All right, exactly same as what we did before. Is okay? All right. So if I open that, where is my, I think that's what is there. So can I show you now tutorials, and then there is a solutions also. Yeah, there you go. Of course, this type of problem, you need a quite time calculator and to do, yeah, those type of things I have there. So this is what we did the first time, but I wrote this little bit colorful so that you know how it is done, right? Look at this, that area, and then you find this is because of the backfill, that's because of the surcharge, and then this side moment, that side moment, yeah, total, vertical, and horizontal, and I have calculated that here, so you can check, all right? Same thing here. This is what the first two terms in the previous problem was 0, right? Only the third term, but I think they calculated I gamma because it's had a very big impact. So this also same, you divide into different parts. You see at the bottom side that, and at the top that part, and then also the backfill pressure, right? And then you calculate. I think it's all good. One thing we need to understand is, right? One thing is we need to understand is for short term, yeah, for short term factor of safety is pi would be 0. So what that means is in the short term is while swell is saturated, so there will be friction angle we assume is 0, but there will be a cohesion there. But if for the long term, because it will drain out, so it will have both C and the phi. Okay, so that's what the concept is, but the problem is very simple. Please have a look. Of course, in your test or things, will not give this type of very complicated one. There will be very simple wall. There will be only few components, right? Yeah. So there will not be that complicated problems like this. But once you solve this, you would understand now what is the process. Yeah. All right. So that's it for today. Yeah, we did all tutorial problem anyway here. Okay. So now, main thing to understand is there are 3 things to check. One is for sliding, another for rotation, and another for bearing capacity at the foundation. Okay, so it will not be hard if you just follow some steps, and then always check what is overturning, what is sliding, and then how much is the pressure, Q max and Q min at the bottom. I think that's enough for today. Yeah. Any questions for me? Another thing is, guys, yeah, Monday. Yeah, Monday, please do come in the campus. So we'll be doing our assignment too. Oh, maybe I'll open that now. All right, this is a good time. Oh, maybe I turn off, so it takes time to post password, right? I have already uploaded assignment 2. That is done by GeoStudio. So because of the license issue, sometimes we have access, sometimes we don't. Please bring that assignment with you in the lab, right? Yeah, and we will be doing that on Monday.
So assignments?
Yeah.
You have uploaded in Moodle, sir?
I think so. Not yet. Can you check?
Yes, sir.
That is already there. Yeah. Okay. Thank you. So that's already there. So just print that out and then bring in the class, right? Okay. So then we will learn few things. Of course, because of this license issue, you see, this is week 6, right? Still, we can't use that. So this is very few weeks to go. I think week 8 is the submission, right? Yeah. So that's why we want to just finish the assignment first, and then if there is a issue, then we will be safe. All right. Okay. So please bring that to the class.
Okay, sir.
Okay. I'll not do that, right? I'll just based on that problem, I'll do one, we'll do one, and then you can replicate that same for your assignment. Okay. So, and then also Tuesday is the lab. They haven't fixed. I'll ask them what time. They haven't said anything to me. So I'll ask that and let you know by messaging. All right.
Yeah, sir. In morning.
That's, I don't know. That's the thing. It's based on the lab technicians. I'm not going there. All right. So they will run the labs. So maybe in the morning, but they have just before they said 30th of August. They haven't confirmed after that. So I'll write to them tomorrow morning, and then they will confirm, and I'll let you know by the Moodle messaging system. Is okay?
Yes, sir.
Any other questions, guys? Yeah, please try these problems, right? But these are all complicated. Everything is there. There will be a simple problem, but you need to understand 3 fundamental concepts for the retaining wall design. That's it. Yeah.
Okay, sure.
Okay, and then okay, I forgot. Yeah, some of you have already sent me the marks of your presentation for yourself as well as your friends, right? So could you please do that?
Marks? I haven't received mail, sir.
What happened then? Some of you got, right?
Yes, sir. Yes. Check your Moodle
Yes,
link.
uh,
Yes, sir.
got,
Yes.
got the mail.
Yeah, please. You
Done?
got that. You don't need to do anything, right? In my email, I have email written there, right? Just in my email, just write team 1, that much, team 2, that much, team 3. That's it. Okay, simple. All right. I want to see how you feel, whether my feeling of the presentation is same as yours or not. Be very like what they call, we call it judge, right? Good judge. That's it. And then of course, that is not final, all right? So I'll look at my evaluation, of course, there, as well as I'll look at the report and then combine total together and release the assignment 1 marks, okay? Please,
I'll
do
do
that.
tomorrow,
Right?
sir. I can't find now. I need to.
Please, yeah, some of you friends, can you suggest him how to find that?
Yes, sir.
So is what? In Moodle, you can check the Moodle messages, right? Yeah.
Yeah, sir. I received.
But
the
email you didn't get from the other system, right? Just the messaging. Yeah, there is just some communication problem there. So I just wrote this morning, I think. Yeah, this morning or this afternoon sometime.
Morning, sir.
But yeah, even if you don't get email, don't worry. Just send me an email in my email address. Don't write to everyone, right? It's confidential. All right. So just in my email, write team 1, that much, team 2, that much, team 2, out of 100. That's it. Okay, no need to do anything. Come on. Yeah. All right. Thank you, guys. Yeah, you have been awesome. Go and see you.
Yeah.
See you
Thank
on
you, sir.
Thank you, sir. Thank you.
Thank you, sir.
See you
So,
next
thank you.
week.